Alright, so now our next topic is projectile motion. We want to study when let's say, when the object is undergoing the projectile motion, how do we analyze its motion? Okay, take for example, in chapter 2, you learn when the object is undergoing a free fall. This basically you drop these things and it's going to falling down. So what happened if, so this is purely in the vertical direction. You also learn that, learn the motion along the horizontal direction. So what happens if you have a motion that consists of both x and y directions? So how do you analyze that motion? For example, if I toss this, and then I'll give you the initial velocity and just toss it somewhere, you can see that it does not, let me just go here, so it does not fall down vertically, it does not go forward, only, it actually traces our trajectory. So for example, like this, and this is what we call the projectile motion. So how do we analyze that? Okay, so let me, before we actually go through the math, let me just draw the diagram. And based on, let's say if we have, if we throw a ball, given the initial velocity, let's say v naught, and then we analyze the motion at like every other second just to see, where it is at, and then look at how the velocity position changes with time. So let's say this is our x and y axis. And you have an object initially at this point, and it's being thrown, and then it's given the initial velocity, let's say, let's say v naught. So it's going to trace out a motion like this. Okay, and that's basically, just like a trace out. This is what we call the trajectory of a projectile motion. So let's look at what are the things that we know? So we know that it has initial velocity v naught, and again, if you want to find the initial velocity, it's always tangent to the curve. So this is the curve. So you have the tangent. So this is your v naught. Okay, and it is as you can see, it is actually at the of the axis, which means that it has both the x and y components. Okay. Now, so this v naught, we're going to use this vector form to indicate that it has x and y component. And it is making an angle theta with the horizontal x-axis. So that's this is your starting point. And we're going to see how, what happens to, to the velocity as a function of time. So this is the total velocity. If we find the s component, that would just be this. So let me just draw a line. So this is your s component, v naught x, right? And then this thing here is your y component. So this is your v naught y. Okay, so it's very easy because to figure out what is expression for v naught x and v naught y, because you have the magnitude, you have the angle that's in reference to the positive x-axis. So v naught x would just be equal to initial velocity and then times cosine theta. And your v naught y would just be v naught and then sine theta, because the y component is opposite to the angle. Okay, so now we have that. So let's say at this instance, when the object is traced out to this point, what happens? So when we look at this, diagram horizontally, even though the object is given initial velocity, so it comes with a non-zero initial velocity in both x and y direction, we have to realize that, in the horizontal direction, there is no acceleration. So there is no acceleration. So, so we'll say that the a sub x, no acceleration. Okay. What about your a sub y in the vertical direction? What is the acceleration in the vertical? In the vertical, we know that it's always experienced the free fall acceleration. So that's our negative g. So this has become very interesting. We have a motion that has the x and y component, has non-zero initial velocity in both directions, but then one direction, the horizontal direction, has no acceleration, and the vertical direction is experience a negative downward acceleration. When you have a negative acceleration, it means that it slows the object down. So what's going to happen is that initially your vertical velocity is this magnitude, because it experienced the acceleration that slow it down. So at this point, you'll find that the upward magnitude is actually getting smaller. How do I know that? Because if you remember, your the final velocity is equal to initial velocity and then plus AT, right? So as time increases, this is negative, which means that your final velocity is going to get smaller than the initial velocity. So at this point in the vertical direction, you have velocity that actually is getting smaller. So this is your Vy. So I'm going to drop the 0 here because 0 indicates that's initial. So this is at any instance that in the vertical you have Vy. And then what about horizontally? Horizontally, because there's no acceleration. If we look back to this equation of motion, if there's no acceleration, the velocity cannot change, which means that the horizontal velocity will stay the same throughout the motion. Okay? So let's say if this is in this case, you still have your Vx, and your Vx is equal to your V naught x. Okay, this is what happens when you have projectile motion because there's no acceleration in the horizontal direction. Now let's look at when it reaches the highest point. At this point, when it reaches the highest point, it means that it loses all its vertical velocity. And so from this equation, you can easily calculate when there's no vertical velocity and you have an initial non-zero vertical velocity, you can calculate how much time it requires to get from the initial non-zero velocity to the zero velocity in the vertical direction. So your Vy here, when it reaches the highest point, it has zero velocity. But at the same time, it also has a rightward horizontal velocity, and it does not change. You still have your Vx. Okay? And then, let's look at exactly at the same altitude. So this is where the object is. What's going to happen is that you still have that rightward motion. This is your Vx. What about your Vy? Now, we can see that the motion actually is going down. If it's going down, which means that the velocity is actually, in the vertical direction, has to be negative. And so you would expect that because it's symmetrical, you will have exactly the same magnitude but pointing in the opposite direction. So this is your Vy, now is negative. Okay? And then when it gets to this point, you will find that you still have your Vx, a bit too large. Still have your Vx, and then you have your Vy. And you can see that they are exactly symmetrical. And then so this is your direction. So your velocity is basically tangent to the curve. So total velocity. Let me just draw the total velocity. You will have something like that. So this is your V, and then this is your V, tangent to the circle, and then tangent to the curve. Okay, so you can see that during as time progresses, you find that the horizontally, because there's no acceleration, it stays at a constant velocity, and that constant velocity is equal to the initial horizontal velocity. In the vertical, this is what you started out with, and then it's going to get smaller and smaller until it reaches 0, and then it's going to come back down, and then if there's room for it to move downwards, it's going to go forward. Okay, so this is how we we just analyze the trajectory motion. You can see how they behave in terms of from the velocity's perspective. So it's going to have trace out like that. Okay, so as you can see, even though it traces out trajectory, that's a combination of the x and y motion. You can see that horizontally, the horizontal motion has nothing to do with the vertical motion, right? Because horizontally it just keeps going forward, going rightward, but vertically it goes up and then goes down. They have nothing to do with each other, and that makes sense because we know that x and y, they are independent to each other. The motion along the x direction has nothing to do with the motion along the y axis. So when you analyze projectile motion, this is something to bear in mind. X component, whatever happened in the horizontal direction has nothing to do with what happens in the vertical direction. Okay, and so after we found that, from this point, the starting point, all the way to where it reached the same altitude. This is there at the same altitude from the starting point to where the going back to the same altitude. This horizontal distance is r, which we call that range. Now you can see that this range is very specific. It refers to the horizontal distance of the object from the starting point to the point where it reached the same altitude. This range may not necessarily be equal to the total horizontal distance that the object traveled, because let's say once the object passed beyond this, this altitude, and then let's say it goes at this point, you can see that it is at a different altitude in the vertical direction. But then horizontally, this is the starting point, and this is where it finally stops. So this position, the final position vector in the horizontal direction may not always be equal to the range. So that's something that students always, sometimes make me say, assuming that the range is equal to the total horizontal distance, which is not always the case. Okay. So now, how do we analyze this kind of a motion? So let me just lay out the equations of motion, because it is the equations of motion that govern how the object moves in the horizontal and the vertical direction. So let me just erase this. Okay, so let me just draw a simplified diagram. So we have a diagram like this. So you have an object that's going like that. Okay, and we define this to be the highest point, and that from this point to that point, that's our range. And we said that this object has initial velocity v naught, and it's making an angle theta here with a positive x-axis. So now let's look at how the velocity, initial velocity in the xy component, the acceleration in the xy direction, and also how the equations of motion has to be modified in response to the different values of the acceleration and stuff. So let's see. Horizontally, and vertically. So again, like I said, even though it looks like they are combined, although it looks like it is x and y are coupled, but then they are actually decoupled. The x component has nothing to do with the y component. So now let's look at initial velocity. Horizontally, we know that based on this diagram, horizontally the horizontal component would be initial velocity, the total initial velocity times cosine theta. Okay. What about y component? The initial vertical component would just be v naught and then sine theta. Okay. So that's basically you have initial velocity. What about acceleration? Horizontally, there's no acceleration, so we put a sub x equals to 0. Vertically, your a sub y is equal to negative g. Okay? Now, what about equations of motion? We introduced 3 equations of motion that use a lot. So let's see how how they being modified. So let me just write down the equations of motion that you learned in chapter 2. You have the final position that's equal to initial position plus initial velocity times time and plus 1/2 at squared. And then you have another one that's called the velocity, final velocity is equal to initial velocity and then plus the acceleration times time. And the other one is that the final velocity squared is equal to initial velocity squared and then plus 2 times the acceleration times the displacement. So those are the equations that you learned in chapter 2. Now let's apply this equation to the horizontal to the projectile motion. The first equation, we can see that our v naught here becomes v naught x, and our a here is 0, so you don't have that term. So what you have here is that your x, the final position, is equal to initial position, and then plus initial velocity in the horizontal direction, and then times time. You don't have the last term because there's no acceleration in the horizontal direction. Okay? In the vertical, we're going to use y to represent the vertical displacement. So you have your y, final position is equal to initial position, and then plus initial velocity in the vertical direction. So v naught y, and then times time, and then your a here, remember, it is a free fall acceleration, so minus 1/2 g, and then t squared. So your g here, again, is a positive value. So ay is negative g. So when you replace your a with the with this expression, you got negative g. Okay? So that's our first equations of motion, and you can see that they are different. This one has a non-zero acceleration. Horizontally, there's no acceleration, so you stop at the second step. The next equation, v final velocity is equal to initial velocity plus at. Again, horizontally, there's no acceleration, so what we have here is the final velocity in the horizontal direction is equal to initial velocity in the horizontal direction, and which we already said that before. Okay, so you can see that horizontal velocity does not change with time; it stays at a constant value because there's no acceleration in the horizontal direction. What about in the vertical? In the vertical, we're going to have the subscript y, so you have v sub y that's equal to v sub 0y. Final velocity in the vertical direction is equal to the initial velocity in the vertical direction, and then minus g times t. Okay, you can see that your a here is negative g. What about the last one? The last one, because there's no acceleration in the horizontal direction, so this term goes away. So basically what you have here is just this. This is exactly the same. The final velocity is equal to initial velocity in the horizontal direction. What about in the vertical? In the vertical, we're just going to add y here, replace our a with the negative g. So what we have here is that you have v naught y squared is equal to, vy squared is equal to v naught y squared, and then minus 2g, and then delta y. Okay, so let's take a minute just to look at how these equations of motion are modified in response to a different situation in the horizontal direction and in the vertical direction. Now, of course, this one, if you express a unit vector notation, you will have the initial velocity is equal to v naught x I hat, v naught y j hat. And this one, you have the total acceleration is equal to no horizontal component, so it just be a sub y and then j hat. Okay? And so that is that. What about the velocity at any given time? The velocity at any given time would just be this, v naught x, because it does not change, or you can just leave it as vx, because vx and v naught x, they are exactly the same. So just use that. So you have your vx component, and then vy component, whatever that is. Okay? So these are basically the equations applied to the projectile motion. Now let's look at, now previously we mentioned that you can find out what the r is. The r is defined as the horizontal distance between the initial starting point and the point where it reaches the same altitude. What does that mean when it reaches the same altitude? So let's look at how do we use that. At the same altitude, what does that mean? It means that if this is your y, so I'm going to define my coordinates. If this is my y here, that's 0. So let's say the object initially at this point. So initial height, I'm going to use I to indicate initial. And then the final height. What is our final height here? Our final height, so initial height, final height. Because the final height is actually at the same altitude, which means that it is again at that same level. So it is also at 0. So in that case, how do we find the time? So in order to find the range basically is equal to this. X minus x naught, that's equal to initial velocity in the horizontal direction times time. So you need to figure out what the time is. How much time does the object take from this point moving to that point? So how to find out time? We can utilize the information that we have here. The final position and initial position, they are at the same level. So you can utilize this equation, okay, to figure out what time is. So what we're going to do here is that you're going to use this. So you have your y, initial height, that's equal to the final height is equal to initial height plus the initial velocity in the vertical direction times time minus 1/2 gt squared. So in that case, this is 0, this is 0, v naught y times t, and then minus 1/2 gt squared. So you can see that your g is a constant, and v naught y, that's in this case, it is is a given, is a known quantity, so you can actually figure out what time is. So t here would just be 2 times the initial velocity in the vertical direction, and then over your g value. Okay, so this is the amount of time. This is the amount of time, that would for the object to take from going from this point to that point. Now, once you have the time information, then we're going to plug into this equation. Okay, so that's how we define this initial point to be 0 here, and the final point is your r. So you have your r that's equal to 0, and then plus initial velocity in the vertical direction, and then times time. So what is our time information? Our time information is this. So we're going to plug that in. So you have times 2 initial velocity in the vertical direction over g. So in other words, the range is equal to 2 times the product of initial velocity in the horizontal and the vertical direction and over your g value. Okay, and as I mentioned, this equation is very specific because it only applies to when you have the situations like that. It does not, your r does not it's not always equal to the total horizontal distance that the object travels. But this is your r value here. Now, in the book, they actually give you a lot of derivations and stuff, but yeah, I mean, it's nice to know them, but this equation, this two sets of equation will be sufficient enough to do every problem. Okay, so let me just erase this. So that's say, if we want to express this in total velocity and angle, how do we do that? Realizing that your Vox is this, Voy is that, so we can actually plug into this equation and see what we get. So you have your r here, that's 2 times your V naught, and then cosine theta, that's your first, and then Voy is V naught sine theta, and then over your g. So what we have here is that we have 2 times the total initial velocity squared, cosine theta, sine theta, and then over the g value. And also using trigonometry, the 2 cosine theta, sine theta, is actually equal to sine of 2 theta. So then, if we utilize this, what we have here is that you have your V naught squared over g, and then times sine of 2 theta. Okay? So, this expression and that expression, they're exactly identical. It just depends on how you express that. This is in magnitude and theta and angle representation, and this is just basically when you have the x and y component, you can do that. Okay. So now, if we look at this equation, what can we tell from this equation? We can see that when theta is equal to 0, basically, there's no range because it will just be at that point you have no angle. What about under what condition that you will have the maximum R value? In other words, the range. This is getting to the maximum total distance. So in order to get to the maximum range, what we see here is that your theta, if theta is 45, then sine 90, because you have 2 theta, sine 90 is equal to 1. This will give you, so your R will just be this over G. That will give you the maximum value. because any other angle that will give you a value that's smaller than the v naught squared over g, because your sine, is your sine theta. Sine 2 theta is basically confined within this value, right? So anything that's less than, so if you have like 50 degrees, when you plug it in, your R value will be smaller than when theta is actually 45 degrees, okay? And that becomes very useful when you want to design something, and then you want to hit the target, and you want to have the to have the maximum range. Then this angle, let's say this is your your device, and this is your target. Then in order to hit the target, you can actually do this kind of calculation in order to find out at what angle that you can actually get the maximum range to hit the farthest object as much as possible. And what we found here is that your theta, has to be 45 degrees in order to get to that the farthest points. Okay. So that's that. What about if we want to find the highest point? How do we do that? To do that, now we can erase this. If we want to find the highest point, again, this is our initial point, and let's say this is our final point. So our final point, that our y here, yf, is equal to h. So how do we find that? So whenever you get to the highest point, it means that the velocity here is equal to 0. So again, you need the information of time. So let's look at in the vertical direction. In the vertical direction, if the final velocity is equal to 0 and you have the non-zero initial velocity, you can find out what time is. And after you have the time information, then plug into this equation, then you can figure out what is the highest point that you can attain. So let's do that. So you have Vy that's equal to V naught y minus gt. So now this is equal to 0. You have this value minus gt, which means that the time that it requires from this point to that point, it's just basically equal to V naught y over g. Once you have that time, then let's plug into this equation. So you have your y. Your y is, so let me just write down here. So y is y naught plus V naught y t minus 1/2 g t squared. And so what we have here is that you have your h, the final position, is equal to initial position, and then plus initial velocity in the vertical direction times time, and your time here is this. So we're just going to do that, plug it in, and then minus 1/2 g, and then you square it. So you have V naught y squared, and then over the g squared. Okay. So what we have here? So what we have here is that you have the V naught y squared over g, and then minus 1/2 V naught y squared over g. So altogether, what you have here is a 1/2 V naught y squared over g. So that's basically the highest point is equal to 1/2 V naught y squared over g. Now, we introduced the expression for range. We introduced the expression for the height. But I would suggest you, whenever you do problem, you start out with this equation, because sometimes the problem can change. This may not always be applicable. So you would start from the most fundamental one. Start with this two-set equation, and then and then analyze the motion to see how to find out time based on the information you're given. After you find out time, then plug into the pertinent equation in order to figure out what the maximum height is and what the horizontal distance or the range should be. Okay, so the last equations that I want to go over is that let me see. So we have that. And I think in the book you also have another equations, and that looks very busy, which so it's just for your information, and I don't. But let me just. Okay, so if we want to find the trajectory of this, let's say the expression for the y as a function of position x. How do we do that? So let's see. We have our y is right here, okay? And if we take this, initial height to be 0 and initial position horizontally is equals to 0, then we can have this. So we have our y is equal to, that is 0, and then plus v naught y times t, and then minus 1/2 gt squared. Okay, this is the vertical displacement as a function of time. Now we want to actually express that as a function of position in the horizontal direction. So how do we do that? We have this. So initial point is 0. So you have your x. So you have your x that's equal to x0, which is 0, and then plus the initial velocity in the horizontal direction times time. You can see that you have two equations. The common factor is the time here. So I'm going to replace our t, use this equation, and say that my t is equal to position, horizontal position over the initial horizontal velocity. And then I'm going to plug into here and there. So what we have here is that we have y that's equal to initial velocity in the vertical direction and then times time. Now the time is this. So you have your x over v naught x. And then minus 1/2 g, and then you square it. So t squared and v naught x squared. Okay, so I'm going to rearrange this. So you have voy over vox times the position in the horizontal direction minus 1/2 g, and then you have your x squared over v naught x squared. Now let's look at this. What is the ratio of the initial vertical velocity to the horizontal velocity? If we look at this diagram, you have your theta here. So this is your vox, and this is your voy. So if you have vox over voy, that just gives you tangent. So you have the tangent theta times the horizontal position, and then minus 1/2, and then you have your g. I'm just going to put it in, okay, g, and then x squared. What about v naught x? So v naught x basically is this. So you have your v naught squared, and then cosine theta squared. Okay, so what you see here is that this basically, we change the variable from t to x. And so this is actually, just for your information, the important equations is this, okay, this equations and this equations. All right, so I think that pretty much cover the projectile motion. As you can see, horizontally and vertically, they are completely independent from each other, so don't even mix them together. So whatever happens in the horizontal does not impact whatever happened on the vertical, and vice versa. And this equation basically, is you combine those two motions together into the two-dimensional motion. Okay.